Welcome. I'm Bob Ward from Microsoft. Welcome to the past Virtual Summit 2020 and talking a little hyperscale. So before we get started, one of the most important things we got to get out of the way is fill out your session evaluation. We take these very seriously, so please take time to give us feedback on what you think about our session today. Well, what is this session today? This session's about hyperscale, SQL Server built for the cloud. And I'm really excited today to be joined by Denzel Ribeiro of our team who works on hyperscale. Denzel, how's it going?
Hey, pretty good. I'm excited to be here as well. My name is Denzel. I'm a program manager in the hyperscale team. Excited to share some of the deep dives and present alongside Bob. Hyperscale is the future, and hope you guys enjoy the session.
Thanks, Denzel. So excited to be here because this is Denzel's focus at Microsoft. And so I've got the expert with me to go deep into hyperscale. You're going to want to know, where do I get resources for our talk today out of the gate? So I'm going to put these links on the last slide today, but just note here, these links I'm listing on this slide, this is where the deck can be found, the demos can be found, and also our Azure SQL workshops for other information about Azure SQL. So what are we going to do today? Hey, we're going to get hyper. This is a level 400 talk. I wanted to put it 500, but I was afraid, would it really be 500? So if you walk away thinking it was 500 or 600, we've achieved our purpose. We're going to talk about why we build hyperscale. We're going to get into some architectures. We're going to talk about how transactions and pages work, how replicas work and failover, and even stuff like snapshot backups. And at the end, Denzel's going to give you some great tips about hyperscale. So sit back. We're going to go hard and fast. In fact, we're going to go hyper actually. So let's start by looking at why we built hyperscale, which we call Project Socrates. So first of all, we needed an architecture in Azure SQL, different than we'd built before, for scaling compute and storage. And one of the things we discovered we needed to do, in order to support really large databases, we need to put the databases in Azure Storage and allow us to do things like snapshot backups. Well, Azure Storage is great, but to get true I/O performance for our customers, we had to build kind of a tiered caching architecture as part of hyperscale, and you're going to see today what we mean by that. Now, in order to continue to make that scaling story possible, we need to kind of separate transaction log processing from page processing. And again, you're going to hear a lot of information today of how we made that happen. And then finally, at the time we started building hyperscale, we didn't have a system where we had multiple replicas, especially to be able to read scale on the fly. You're going to see a really cool demonstration from Denzel today of what that looks like. This is kind of why we built and why we call it hyperscale. So let's dig right in and talk about some architectures. You may have seen this presentation before, and I kind of consider this a high-level architecture diagram. In this tiered architecture, we start with something called compute nodes, where SQL servers run on here just like a SQL server today, except there's something called a resilient buffer pool extension cache, which is like SSD drives, where we store information about pages, not in the buffer pool. And you're going to see today, especially when Denzel gets going on his presentations, what does that actually look like internally? Now, as part of this other architecture, if pages can't be found on these compute nodes, these pages are also put on something called a page server. So these are SQL servers dedicated to hosting pages, and it is a remote call to get pages from them, but it allows us to be able to store large amounts of data in this tiered architecture. Now, the actual data files themselves are stored in Azure Storage, and we rarely have to go to these data files because usually things are available in these other tiered parts of the architecture. But putting the data files in Azure Storage is really significant because it's going to allow us to do something called snapshot backup and restore, which gives us really cool capabilities for point-in-time restore operations. Now, what about the transaction log? Well, the transaction log runs on SQL servers on the primary node, but we separate log processing to something called the log service, and we store the log separately from the data files, both on Azure Premium Storage and something called the landing zone, and then for point-in-time restore operations for retention purposes in Azure long-term storage. And you're going to see more in detail of what that actually looks like. Now, this log service, as it sees these changes, is going to feed the page servers and the secondary replica nodes to get changes so they're up to date with what's going on in the system versus relying on SQL Server having to push those changes to those layers. Now, failover is going to work a little bit like Azure SQL and other areas of the infrastructure using things like Service Fabric. But here's what's interesting. You don't even have to have replicas to do failover because since the data files are in Azure Storage, we can simply put up a new node for your primary replica and then feed the data from page servers and from Azure Storage itself. But if you have secondary replicas, since we're keeping these up to date, failure can be quite fast. And so failover time is dependent on existence of secondary replicas. Now, one of the things you're going to see when you look at Azure SQL Hyperscale is you're going to see some differences in how we account for things from an I/O perspective. So common DMVs you're used to seeing, as you see on my screen right here, are going to show you some of the differences about how we look at things like the resilient buffer pool or something called page servers. And in fact, let's just get into a demonstration. Why not go look at an Azure SQL Hyperscale from how you're going to see that from your point of view? Because we're going to show you some demos later of the internals that you probably won't see as you're going to look at a hyperscale deployment. Okay, what you see here is a management studio connected to an Azure SQL logical server with several different Azure databases. And in this particular case, I've got a hyperscale deployment that I'm connected to. And hyperscale itself has no maximum sizes from a storage perspective. You don't even tell us the max size. Like other Azure SQL deployments, we just create the size for you. And if you look at something like sys database files, you're going to notice here that you're going to get, in many cases, when we start building the initial database, like 4 files. We could even have more depending on the size of your system. And you can see here, there's like 4 10 gigabyte files where we're going to store data initially, even for a small hyperscale database. Now, if you want to see the limits of what you have in Azure SQL deployment, you look at this DMV, DM user DB resource governance. And so if I run a query here for hyperscale, I can tell already for this hyperscale, this is something called a slow name or service level objective. This tells me I'm running a hyperscale Gen 5 hardware with 2 vCores. And in fact, the CPU limit backs up how many vCores I have. Now, unlike other Azure database deployments where the max database size is dependent on something you choose, notice here, it's like 100 terabytes because hyperscale is literally unlimited storage. Now, you have transaction log rate limits when you do many different Azure SQL deployments, and hyperscale is at 100 megabytes. And we'll see later a little bit how log governance works with Azure SQL Hyperscale. Now, we don't give SQL Server the entire memory footprint when we deploy Azure SQL. So we're going to use something called a Windows job object to give you the true memory limit of your deployment. And that memory limit is going to be dependent on this service level objective. So for 2 vCores, you can see for hyperscale, I got about 10 gigs of memory available to me. Now, when you go run queries in this tiered architecture, because of the fact that you may be limited on memory, it could be we need to pull pages for your query from buffer pool locally, from this resilient buffer pool cache, or even from page server. So I thought I'd show an example of what that looks like. And we talked about how virtual file stats may look different in a hyperscale environment. Notice this. So first of all, you've got something called file ID 0 and database ID 0. What is that? Well, that's the resilient buffer pool. And you can tell we're tracking how many reads come from that resilient buffer pool. But notice also here, we're tracking writes. Well, why do you have writes? Denzel's going to explain that later. But basically, this is us feeding things into that buffer pool extension on an SSD on the local compute node based on query access to the buffer pool in the local compute node. What about these other files? Well, you can see here, you have 4 other data files. These other data files, in the case of hyperscale, are the page servers. So any reads we're doing here for these files are representative of situations where when you run a query, we have to go after our page server to service the query. And if you see a lot of this, it could be an indication that after running a hyperscale for a while in a warm scenario, you probably need more memory for your local compute node. Now, one thing I want to show you here is that while we have 10 gig of memory for the local compute node, the resilient buffer pool is actually 3 times the size of your memory limitation. So notice here, this resilient buffer pool SSD file is like 30 gigs on that primary compute node. Now, we mentioned as well that there are other statistics for queries that you may see. So here's an example of a query I've run against this hyperscale. And notice here that with set_stats.io, I still get things like logical reads, but I'm also going to get information about page server reads. So in this particular case, you have read-ahead reads. This is an example of doing I/O from the resilient buffer pool, and I have page server read-ahead reads. So in this particular query example, I'm reading both from the buffer pool, from the local resilient buffer pool cache, and from page server read-aheads. So these are just examples of some of the diagnostics we give you. And this is what you might see from the perspective of looking at a hyperscale deployment. Well, hey, now that you've seen a quick demonstration of what it looks like from a user point of view, let's let Denzel dive a little bit deeper into the nuts and bolts of how hyperscale works.
Thanks, Bob. Let's take this a step deeper and cover kind of the flow of data between compute and the different components of hyperscale. So Bob went through a bunch of these points, but just let's see how the data flows. As the legends indicate, I've denoted log flow in red and the data pathways in green. So user comes and all your connections from a user perspective are to the compute node. All your writes from a compute perspective land up in a log service. There is no connectivity from a write perspective between your primaries and your replicas, or your primary and your or your primary compute and page servers. All the flow of anything inserted, any DML, goes to an external log service. And the log service then communicates with page servers, or rather the page servers communicate to the log service and request for logs from the log service. Each of these page servers are modeled as service fabric applications. Each of them have built-in resiliency. There's a replication factor of 2. Each of them are 128 gigs in chunks, and their chunks, just like Bob showed in virtual file stats, they correspond, each of these page servers currently correspond to what you see as a file on compute. Right, so you have 1 to n of these up to 100 terabytes, and log flows to log service, and page servers actually pull that log and apply it to redo operations. Each of these page servers, including each of the replicas, also have a file on blob, which we'll cover a little more details about that later. And then the log service, last but not the least, also has to copy log to a blob or long-term retention for pitter or point-in-time restore, purposes. From a get page perspective or get data perspective, when compute does not have the data it needs in its buffer pool or caches, it requests data from the page server, and that results in a remote page server read. And last but not the least, secondary replicas also consume log from the log service. Not all the log is applied. Log is only applied corresponding to the pages that exist in compute's buffer pool or local RBPX. So if you're ingesting data on primary, all those changes do not go into compute unless there are queries that need pages that require those LSNs that have been modified. So let's go to a demo looking at the topology of hyperscale. Okay, so what I'm going to show you right here is something called one box. And this is so that our developers can simulate a hyperscale environment within one virtual machine or a single machine and do some level of functional testing. And so a lot of what you see here, from a settings perspective is not necessarily what is in production, but I wanted to give a gist of kind of how the topology of hyperscale works, how the different components interact. And as this is a 400 level session, we will put breakpoints and look at flow of information between different components. So first, I'm showing Service Fabric Explorer. And in Service Fabric Explorer, you will see we have modeled 3 Service Fabric applications. One is the compute. The first one is the compute. And for a compute, you see a primary and a secondary. And this really depends on the fact that you have more than one replica provisioned. If you just had one replica provisioned, all you would see is a primary. So this is not modeled. There's no built-in resiliency from the perspective of, unless you've chosen an additional replica. Then you have the storage layer, which is the page servers. On the page servers, we have built-in resiliency. There are 2 replicas. You see node DB1 and node DB3 as the 2 replicas. One services as a primary, the other as a secondary. Both of these, from a page server perspective, are active in the sense that both of them service requests. Right, and the Xlog is a stateless application which has just a primary replica. So if you click on any one of these, you will see that From a service fabric perspective, we have a target replica set size and a minimum replica that it considers as required for this service fabric application to be up. And then you have health perspective. And Service Fabric actually gives the ability for some of the failover on Azure. So you could failover a replica even without having availability groups. So that is at a very high level, the topology from a Service Fabric application. So now Bob will take you through some transaction log hardening and even dig deeper into how Hyperscale hardens the log. Over to you, Bob.
Hey, thanks, Denzel. I love that peering inside of one box of what actually Hyperscale looks like under the covers. Let's spend some time talking about transaction log and Hyperscale, and then Denzel will talk to you about page life cycles and how page servers work and the resilient buffer pool. So in a normal SQL server, when you write to the transaction log, you write typically to a local file. In the case of Hyperscale, let's focus on these arrows and talk about log hardening and log changes. So hardening of flushing the log for SQL Server, the same rules apply for the wall protocol or for commits and so forth, but the log is remote from the primary. The transaction log doesn't actually exist in the primary node, it's remote. Hence this purple diagram here pointing to what's called the log service. And then these page servers and replicas will pull changes as processed in this log service to feed their system. So pages are updated on page servers based on log changes and replicas as well. It's a little bit like availability groups, but it's not quite the same. That's a push system. This is a pull system. It's still going to use similar technologies to apply log changes to update pages. Now notice here I commented that the log service is stateless, and we'll talk about exactly what we mean by that. The log itself from a storage perspective is tiered. So when I have the diagram here for these green boxes, what I'm talking about here is something called the log service cache, which is stateless. It's just used for log service processing, which we'll show you in a second. And also what's called the landing zone, which I talked about earlier in this presentation. This is truly where the transaction log is from a remote perspective. So when the log is hardened from the primary node, it's written to this landing zone in Azure Premium Storage. Now we have backup protection policies, right, for days at a time. So long-term storage for Azure is in standard storage, and we keep that around for point-in-time restore operations, which we'll show you a little bit later in this presentation. So you kind of see how the pieces work. It's going to use the components of SQL Server, but with a separate log processing architecture. So let's dive more what that looks like. But before I talk about that, you may wonder yourself, remote log, how do you even do that? Well, we've done this before. And we show a diagram here for SQL 16, but I think this even started back in 2014. And that is when you create a transaction log or database, you can put in a URL for Azure Storage, and we literally now will put the files in Azure Storage and write to them. Now you may be wondering, how do we do remote storage? Well, we've done this before. In previous versions of SQL Server, we announced the capabilities of putting files in Azure Storage. Now, this isn't a managed disk in Azure Storage where it looks like a local disk. This is actually remote blob storage, where we're going to store SQL Server database and log files as page blobs. And in fact, if you look at this diagram right here and this syntax, when you specify your database and log files with HTTP addresses, we're going to take our file control block architecture and we're going to turn that into something called XFCB or XStore file control blocks. And therefore, things like write files in the Windows operating system will get translated into Azure Blob REST APIs to write and stream data. So we've used this technology before, and we're going to use this in Hyperscale. So let's see how that works. So first of all, the log service, the concept of the log service is there's a single producer or writer from the primary node with multiple consumers. And that could be the landing zone to write things in Azure Storage or something called the xlog process on this log service node. So let's look at a visualization of this. First of all, today you're used to seeing this. In SQL Server, the log writer takes a log block and under commit or for write-ahead log wall protocol purposes, we flush blocks to storage. Well, in Hyperscale, what that looks like is we use a protocol called the Remote Block I/O interface, which uses that same Azure XFCB protocol to write things to Azure Premium Storage. And we call that the landing zone. Now, based on how we age and see things going on in the log, we can destage that to the long-term storage. So this allows us to keep logs both readily available on premium storage for fast I/O and long-term storage for things like point-in-time restore operations. Now, what we do as part of this remote block IO protocol is we'll asynchronously notify a separate program running on a different node called the log service. And in that log service is something called the xlog process. This xlog process has a staging area, which is memory, where it receives these buffer of log blocks. And then the xlog process will organize these in a hash map for easily lookup purposes when other processes need to find log blocks. Now, this is memory, right? So there's only so much can be kept here, which is why the log broker, this process, needs a local SSD cache to put other log blocks if it fills up what's going on within its log broker area. So you can kind of see how the pieces work together. You store your log on storage, but the xlog process is also taking these log blocks. But why does it need to do that? Well, it's because it is the way a secondary compute and a page server will request log changes based on LSNs to say, hey, give me log blocks. I need to update myself. And how does a log broker do that? Well, it could find it in its hash buffers. It could find it in local SSD cache if it couldn't find it there, or it could find it in the landing zone, or even in long-term storage if it needed to. That's why it's called a tiered layered architecture to get log changes. So this is the uniqueness of how we've taken the combination of SQL log writing and put together a different architecture for hyperscale. Now, one other topic for logging that we should talk about before we do a demonstration is log governance. Now, this isn't specific to hyperscale, but there's a few differences on how we do log governance versus other Azure SQL deployment options. So we have something called a limit or a cap based on a resource governor that we deploy inside of Azure. This cap is based on your service level objective. And I kind of talked about that originally when I first showed a demonstration. And you can find that in this DMV, DM User DB Resource Governance, called the primary max log rate. And even there's a way to monitor your usage. You can use other DMVs unique to Azure to see what is the usage of my log compared to this rate. Now, if you look in this diagram right here, I've got primary compute being a node and a SQL server running in it. And inside that node is also another process called the log throttling service. So imagine this, a user generates a log record towards your primary compute node. And then we inside SQL Server are going to generate log records based on this change. What we can do is we can look at our current log limit and see, have we reached the limit based on a rate that we're kind of processing? If we've reached that rate, this is going to result in a weight called the log rate governor back to the user. But this happens even before the log block is flushed. Once that weight has subsided, then we can take the log block, and per normal SQL Server hardening rules, log writer can write this out after a commit or while protocol occurs for the log block. And this is written to the landing zone or premium storage. But notice here in this diagram, if there's a delay in hardening, that's a write log wait. A log rate governor is before even flush activities occur. Now for hyperscale, we need to make sure everything is catching up. And if these different types of services are behind in applying the log, our log throttling service may lower the limit, what you normally see from your primary max log rate, to make sure they catch up. If we detect when we're generating log records, this limit's lowered because of those conditions, this is going to result in something called an RBIO wait. And Denzel's going to show you a little bit later the specific what that looks like. So with this in mind about the log service and log governance, let's take a look at a demonstration kind of what that looks like behind the scenes. Now we got to show you call stacks in a 400 level session. And I thought you might find this interesting. Denzel helped me capture this. This is call stacks from a normal SQL Server log writer that is writing to the transaction log. Now notice here, here's the log manager that's going to write it out. And we're going to use this FCB we talked about earlier to do that file control block. And this is going to result eventually into here, a call to Windows to write out to disk our log changes. This is a standard call stack we see in a SQL Server. What about this XFCB scenario, or in particular hyperscale RBIO? Notice that this call stack, it's still a log writer, and we're still using this file control block here, but this gets translated in hyperscale to this call stack for RBIO. That's that protocol I talked about. Now, what does that do? We still get to use XFCB behind the scenes because the log is remotely on storage, not in a managed disk, but in remote storage as a blob. And then behind the scenes, our code right here is going to use REST APIs to write out the data. So it's a great example of the log writer is a little bit, doesn't really understand it's even writing to this remote storage. Our layers under the file control block structure actually handle the architecture for figuring this out. What about this log rate governance I was talking about? I also am connected here to a different hyperscale server than I did before. And I kind of want to show you a quick example of this. Now, if you want to know what your log limit is, which I mentioned earlier, I can use this DMV right here to go find out. It's around 100 meg, like I talked about. And I've got a workload here that on this huge number of core processor for hyperscale is going to do like a bulk operation, like a select into. So let me kick off that workload right here using OStress and see the behavior of the system. So I'm going to join not just ZM exec requests and sessions, but I'm going to join OS waiting tasks because I know this is in parallel. And if I run this over and over several times, you're going to see what's going to pop up is you're going to see a log rate governor example can hit because of the fact that I'm getting throttled. I'm getting throttled because I'm generating enough log limit on these cores based on these bulk operations to get somewhat throttled. Now, if you want to say to yourself, well, how much am I using getting near this limit? This is where I'm using a DMV specific to Azure called DM Resource Governor Workload Group History EX. That's a mouthful, but it's a snapshot over time of my usage. And now can you see here, my log rate is up near that 100 cap that I'm seeing. You can also see as a percentage from a DMV specific to Azure called DMDB resource stats. So if I run this query here, I can see, oh, I've hit like 100%, which explains why I may be seeing weights from log rate governor. So you can look at things like DMOS weight stats, which you're used to seeing. And if I look for the word rate, I can find out how many throttles have occurred for log rate governor. You even have the ability for DMOS performance counters to get information about bytes that are governed since the startup of the server itself. So great example of log rate governance. If I were to introduce multiple replicas here and change some of my workloads, I might even start seeing what are called RBIO weights, as we mentioned earlier, that the log throttle service kicks in. This log rate governor example is an example where this is independent of hyperscale. An Azure SQL Database general purpose or business critical deployment could also see this type of governance. So a great example of looking internals of how we do things in transaction logs perspective with Azure SQL and Hyperscale, slightly different, but the same as SQL Server. Now, let me let Denzel start going over maybe about the lifecycle of page, how page servers and resilient buffer pool works in Hyperscale.
Thanks, Bob. In the journey of a lifecycle for page, the first thing to have to understand in detail is RBPX. And this is the non-covering RBPX, which exists on compute, not on page servers. So generally, when we access a page, if the page is in the buffer pool, the page is returned. If not, it uses the FCB or file control block to do a read on the disk. RBPX or resilient buffer pool extensions intercepts these read and write calls, which is FCB async read if it's a single page, or scatter read if it's a read ahead of multiple pages, or write, the equivalent in write. And then either reads or writes and sees if that page exists in the RBPX cache or not. So we have a page table. All the RBPX metadata is stored in memory optimized tables. We have something called a page table that stores the database ID, file ID, page ID of pages that are cached, along with an offset into the file and the timestamps. The read is extremely quick. Similarly, from a write perspective, we have a free list, and when we are writing a page into the cache, if there is a free buffer, we will write it into the cache. On compute, this RBPX is a non-covering cache, which means it isn't all the 128 gigs or the size of the database which is covered. All your IOs into RBPX, given it is buffer pool extension, are in pages or 8 KB. So even a read ahead on RBPX is translated into multiple 8K IOs. The size, as Bob had talked about, is 3 times the memory of the service objective. And then we have an LRU, or least recently used eviction policy. When the free pages are below the 2% threshold, we start evicting things from RBPX until it reaches around 10%. Also, one more thing to consider is when we dirty a page or we update or delete a row, and that page is in RBPX, it is invalidated so that an access to that page doesn't give us a wrong version of that page. And checkpoint actually flushes any dirty pages from buffer pool to RBPX and clears this dirty bit. So let's dive into a demo and see how this works. Back to the one box, and let's take a look at the processes. We had looked at the Service Fabric Explorer view of things, and we see that each page server has a replica, and each page server is actually running SQL Server.exe. So you have multiple SQL Server of EXEs, one for each page server replica, and then one for each compute instance. So hence the multiple page server.exes. In addition to that, you also have an xlog process, and the xlog process doesn't run SQL Server.exe, it's its own executable. So those are processes. In one box, they all run within the same host, but that's not true in production. They are spread across different nodes, as we've seen from Service Fabric. Now let's take a look at the files. If you look at the files on the compute instance, you see in this case, I have two data files indicative of two page servers. And I've taken out the size because the size is a little different on one box. And there's plenty of space in this case. Looking at the files on the data directory itself, we'll see a couple files here. We'll look at buffer pool extensions pretty soon, but you see a file for the buffer pool extension, 1 terabyte in size. And then you see the files, the MDF, LDF files for the database itself. But looking at the file properties themselves, this is a sparse file. While the file is 1.36 gigs in size on disk is only 128 KB. Moving on to buffer pool extensions, this next set of statements are really internal statements used to demonstrate kind of the caching into buffer pool. Buffer pool extensions on compute is a non-covering cache. So I've already cleared the buffer pool and RBPX. And so I'm going to show you some of the metadata to do with buffer pool extensions. First thing we'll see is the file path. We already saw the file in question, the RBP file, which was 1 terabyte. The second thing I'm going to show you is the config of buffer pool. You see that this is a non-covering cache. If you look at this on page server, it'll be different. So this is a non-covering cache and gives you the size. The third thing I'm going to show you that these metadata about buffer pool are memory optimized tables. And so the way we'll see that there's no memory optimized table ID itself, but what I can show you is the checkpoint file pairs. HKV2 is Hackathon V2 storage, and you see the checkpoint file pairs, and some of them have free space, some of them have data, right? And then you see the XTP transaction stats below, which show you the total count, read count, and total aborts. The memory optimized transaction stats or XTP transaction stats. But most importantly, one of the main tables that keeps metadata of what is in RBPX is called this DMIO RBPX page table. So running through that, you will see that it has a file ID, a page ID, an offset into the file for that page, and then the LSN of that page and the state and timestamp that it was last validated or invalidated. A better query in this realm, and I'm going to actually filter out some system objects to show you that we don't have user objects currently in RBPX, is I take that table and actually join it with the DMDB page info to get some information about what object this page belongs to. And we'll see that there's no data in this RBPX table the moment it comes back. It's going through the whole RBPX. But we see we don't have any user tables because I've filtered the system tables. So what I'm going to do is actually run, select consta from a user table. And actually, I'm used to putting this go to, but I might have to run it a couple times because it doesn't seem like ADS honors the go multiple. So I've run this a couple times, and let's see if this data is cached. As we've talked about before, RBPX caches a buffer pool only when it's touched multiple times. So it's not on the first access. First access, if you're reading from a page server, it goes into buffer pool directly, not into RBPX. So let's see if this is currently cached in RBPX, and if not, we might have to touch it another time. And it should ultimately be cached in RBPX. You see the events table now. Index ID 2 is cached because it used that for the count star, right? So, so how do I know now if I'm pulling this data from RBPX? So what I'm going to do is I'm going to drop clean buffers to remove these pages from buffer pool. Because in order to read, it has to end up in buffer pool. So I'm going to remove these pages from buffer pool. And then I'm going to break on the debugger on compute. And I'm going to enable this async read function. So I'm just going to enable this and hit a go. And once I do that, I'm going to come back and actually do the same read that we've done before. And we should see that this is actually broken into the debugger as part of the read. And I'll show you the call stack in a second. I'll zoom into it. And we'll see that, okay, it's doing a bpool get. It's doing a get from disk. It reads the FCB async read, the same thing that Bob talked about from a write perspective. FCB async read then goes into RBPX and does an RBP FCB async read. So this is taking that page table entry and going to that offset into the file and actually reading from RBPX. So let me disable that breakpoint, and so we can proceed. So that is kind of RBPX caching or reading from RBPX. I am not going to spend a whole lot of time on virtual file stats because Bob has already demoed. It's file ID 0, which has RBPX and has the stats. And the way to get a diff is to actually run a diff on virtual file stats and actually see the difference between two snapshots and get the IOPS and so on and so forth around kind of the file utilization. We'll see a little bit of that when we do the read scale demo. The other one which is important is we have a performance counter around RBPX, which gives you the RBPX cache hit ratio. So that's the cache hit ratio of how much data are you doing remote reads versus RBPX. And then we have a memory clerk, which has to do more with the memory consumed by the memory optimized tables for RBPX metadata, right? The next thing we'll see from an RBPX perspective is I'm going to cache this TBL NBA. So I'm going to run this a couple of times so it's cached. And then I'm going to actually update this this page so as to create a dirty page. So before that, I'm going to go break into the debugger and enable this notify dirty, RBPX notify dirty, and then go. And so when I update this page, and this is Clippers who didn't win this year, so we'll hope they win in 2022. Better luck next time. And if we go and look at the call stack, because this page was updated, we will see actually the buffer pool touch. When a page is dirtied, it notifying RBPX, since this page was in RBPX, to invalidate it from the cache so that you're not serving up a page which isn't valid. And I don't have time to demo the checkpoint, but when checkpoint executes on compute, it would actually clear out the dirty bit and flush that version of the page to RBPX. So that is all from a compute perspective. We will see a little bit more from a page server perspective. So let's take a look at the page server now. Page server, again, is a service fabric application. It's stateful, has a replication factor of 2. What you need to know is each of these are independent of each other. These do not communicate with each other. Each of them have their own file on Azure Blob Storage. Each of them actually does its own log apply. And then compute actually can talk to either of these in an active format. So it compute maintains a quality of service in terms of communicating with each page server, so it knows the response time from each page server, and if one is down, it will just go to the other one. So it could talk to each. So both of them are actually serving requests at the same time. The page server, unlike compute, is a fully covering RBPX cache. It caches segments instead of pages. So the reason why is because it's fully covering. When it needs to be seeded, so let's say a page server instance or node that constitutes a page server totally crashes. It's an unplanned failover. So we spin up a new page server replica, and it has to seed from cache. So because it is a covering cache, it has to seed this whole 128 gig chunk of your file, which is the file. It seeds in segments. A segment is nothing but a contiguous set of pages forms a segment. The other thing that the page server has is it has kind of a concept of a host data file, which is nothing but a bootstrap type of file, and a concept of a foreign file. And this foreign file actually is the file that talks to Blob. This is the file that has the 128 gigs of data slice of your database, right? And page server offloads some of the operations that otherwise would have happened on compute. For example, checkpoints on compute do not checkpoint to page servers. They just flush 30 pages to RBPX. Similarly, backups that actually happen on other tiers on the compute node and require processing power on Hyperscale do not happen on the compute node, rather happen on page server. And Bob will go into backups in way more detail a little later. And then the job of the page server is actually to request for log from Xlog and apply this log so as to redo all the changes that happen in compute and bring these pages up to speed. Storage redundancy. So we talked about page server compute redundancy is done with Service Fabric. Storage redundancy is handled by the storage layer. So one of these page server accounts at least is RAGRS. So that is replicated across regions and enables the geo restore scenario, where you can restore a hyperscale database, and it's faster if you use the paired region because that's where the storage is replicated to. Deals it. So let's put this together and look at the page read lifecycle. If there is no replica and a replica is bootstrapping, it reads data from Azure Storage, right? So async seeding will populate if it's a new page server starts. After that happens, the page server is a covering cache, so it has all your data. Irrespective of if compute has it, page server has it, and page server's local SSD actually has it. When you issue a read request, a user issues a read request to the compute. The compute first checks, hey, do I have this data? And this IO actually doesn't have to exist in any one, fully in any one tier. It can be a combination of, hey, it exists in buffer pool or it not. If it doesn't exist in buffer pool, you check RBPX and see, hey, do I have an RBPX cache hit? If I don't exist in RBPX, then I do a get page at LSN. So I access a page on the page server. I tell the page server, go to the right page server, first of all, because I know what file I'm reading. I know what page I require. So I go to the right page server and I say, give me this page at this LSN. If the page server is caught up to this LSN, it returns the page. If it is not caught up to the LSN, because a get page at LSN guarantees that the page server will return a page at or above the LSN. If it's not caught up, the page server then does a get log block from log service, applies that log, and returns the page. So that's the sequence of events. Now, one thing to know is once you do a page request, you're waiting on page IO latch. So you don't have the visibility necessarily if a page server is behind today. Right? So this includes kind of the step of page server returning this page or applying this additional log. So once that is done, page is returned and all is good. The next thing we talked, Bob covered log rate governor and log throttling on compute. I'm going to cover specifically some of the aspects around hyperscale. So the compute node has a SQL Server.exe. We also have a throttling service that is running on the compute node. And what does this throttling service do? It effectively communicates with Xlog, and every 30 seconds goes to Xlog. And then Xlog gives it a list of all its actors, which are page servers, secondaries, geo-secondaries, and the last BSN that is applied to those actors. So effectively, the compute knows what is the last LSN or BSN I have generated because all the write traffic comes to compute, and it knows every component and how behind they are. And so then a decision is made to throttle or not. And the reason is we don't want to have some of these components be so far behind that on recovery or an unexpected shutdown or things of that nature, unplanned failover, that we can't meet recovery points which are realistic, right? So we start to throttle if an actor, a page server, or a secondary is 1 gig of log behind. Right? And how much we throttle on is based on a more complex set of heuristics, and because we are changing some of those, I'm not going to give you the exact rates, but it depends on how soon we are catching up, because we know since we get this snapshot every 30 seconds, just like virtual file stats, compute throttling service does a diff of the snapshots and knows what's the catch-up rate of each of these actors. And you know how far you are behind. And so based on those two things, we decide whether to throttle log generation rate on the primary. And if we do, you get this set of weights. Log rate governor, Bob already talked about it at length. But you have these RBIO set of weights. RBIO storage meaning page servers behind. Replica is behind. And this destage is the part where log service is destaging, either to LC, which is local SSD cache, or LT, which is long-term storage. And this article here at the bottom has details on these weights and a whole lot more about IO. So let's go and now take a look at what happens behind the scenes with regards to page servers and the throttling service. On the page server, looking at database files, we see what we discussed in the slide. Each page server has a file ID 1, which is an MDF, and a file ID 3, which is the foreign file. And that's the file that resides in storage. The RBPX config is a little different than compute because this is a covering RBPX. It has all the data. And hence, when we actually populate or seed the page server, RBPX, we seed in segments and instead of pages. And these segments are nothing but a range of pages that are needed to seed RBPX. Now let's go and see how log is applied to a page server. So the first thing we will do is break here and enable a breakpoint which shows us how page server actually gets log from Xlog. As you can see, this is immediately hit, which means that whether you have log generation rate or not, page server periodically or very often in a loop requests for log. So it issues a get next log block from Xlog, which translates to an RBIO log read block, which will go to Xlog and say, hey, do you have a log block for me or not? Right? So even if I hit go, this breaks again, and same stack. So it's a process of page server going to Xlog and requesting for log. Disable that breakpoint. And now we'll move to the next phase, which is enabling a different breakpoint and see how this log apply actually works. So we go to compute here and do an update of a row. And doing an update of the row will update an event table and a specific row. This broke in the debugger, and we can see that this is the same update we executed. It's modified columns, right? And looking at the stack, this update is effectively moving up redo. So it's redoing the LSN changes that compute sent to the log service, and page server has requested from the log service and applying it to the pages, its slice of data, if that LSN is applicable to that slice of data. Let's look at throttling from the compute perspective. So compute periodically requests from Xlog progress of all page servers or actors in the system. And the way it does this is using this SP get actor progress. It's not a stored procedure. It's actually a call into Xlog that invokes or gets the actor progress. And running to this, there are a couple stages you need to, this page server or role 1 is storage, role 2 is primary. So looking at these results, we can see that this role 2 is primary and role 1 is to page servers. So while I'm doing this, I'm actually going to switch to another machine and start a workload. Right. So once that comes, I will look at this. So every actor reports its progress, and you can see for every actor there is an LSN. And compute knows what LSN it is currently at, which is 538, right? And other components know what LSN they have applied. So for example, these two are page servers. We ran this again, and the page server now, which is broken in the debugger because I had a breakpoint, is now not applying log. So looking at this LSNs, they're deviating now. This is the page server which is at 3A0, whereas compute is at 530. Similarly, if I look at their current BSN, they are going to start to deviate. This is 472, this is 072. So compute can then calculate the distance between the actors, and given it has the prior snapshot, the rate at which this distance is covered. Right? So that's the thing. And looking at if we run it again, that distance should be even greater. Yes, it's greater. It's from 3B2 to 3B4, and significantly more log is behind. So I cleared the RBPX and buffer pool, and the intent is, can I read if one of these page servers is down? So I'm going to issue my read. First, I'm going to break into my page server, and then I am going to issue my read, which is a select star. Since the data is not in cache, it shouldn't return if it could not actually get data from the other page server. So if we look at the results and show plan XML, and we go to actual page server reads, you should see that this is a non-zero value. So you see, it got page server reads, though one of my page servers was not even servicing requests because I was broken into. This is because compute maintains a quality of service or QoS to both page servers, and if one page server is down, the other services requests. When we talk about read scale replicas, If you choose to have replicas, more than one replica, they are hot failover targets. In spite of being able to use them for read scale, they are hot failover targets. So our SLA that we have with greater than 0 replicas is higher than the SLA with just a single primary. They're also priced with Azure Hybrid Benefits or AHUB. That's roughly a 30 to 35% discount from replica with regards to read scale. And then the replicas apply log just like page servers do, with one distinction. They don't apply log to every page that has changed. They only apply log to pages that are in their buffer pool or RBPX. Because if a query comes in that requires a page that is not in their buffer pool or RBPX, you can just go to the page server and request that page. And once that page is then in buffer pool, if a change is made, then redo will apply that log to the page server. So there is no data connection. There's no connection really from primary and replica. So there's, no data. All the log changes do not flow. So if an app cannot have latency in terms of even a few milliseconds behind, then it needs to query from primary. If it needs the latest data that is ingested to the last microsecond, you have to go to primary. RBPX cache also on secondary is separate than RBPX cache on primary. So it's cached only based on the workload that runs on the replica. And remember, one of the big things that folks are not necessarily aware of is that max stop can be set differently on replicas. The database scoped configuration allows a different setting of max stop on replicas. And read scale out today enables up to 4 replicas.
So snapshot backups are an important part of the scalability of hyperscale, the ability to do snapshot backups and help speed up point-in-time restore operations. So let's spend a few minutes understanding how snapshot backups work compared to SQL Server normal backups. You see in this diagram right here, I've got 2 different ways of visualizing this. Now, I mentioned earlier in the discussion that we support SQL Server files, the MDF and LDF files on Azure Blob Storage, and we get to use, because of that, the power of Azure Snapshots to do very, very quick backups. So you can see on your screen here, I've got 2 different SQL servers. Now, I've got one SQL server on the left where the database file, like the database, the MDF file, is local to the SQL server. Now, remember, that could be an Azure managed disk. So it doesn't have to be a local disk drive in, say, an Azure VM, but an Azure managed disk, the SQL Server views the database files as a local file. So it uses a write file call in, like, say, Windows to write to the database. Now, in this case, my database file is 100 gig in size, but I'm only using 10 gig. And you probably know in SQL Server backups that when you back up a database, we'll only back up the used portion. So the size of the backup is relative to the size of how much space is used in the database. Now, in the case of SQL Server backing up to Azure Storage, which you can do in any SQL Server, we're going to use this backup to URL concept. And when we do that, we're going to stream 10 gigs of data using REST APIs to Azure Blob Storage. So therefore, the backup file takes about 10 gig of space. But the time it takes to back up this database is based on the time it takes to stream 10 gig. Now, what about this snapshot backup in Azure Storage concept? In this case, the database file is on the actual Azure Blob Storage, like I showed you earlier in this presentation, and we're using that XFCB protocol, which are Azure REST APIs. So when you read and write from this database file, it's not local to the SQL Server, it's not on an Azure managed disk, it's in Blob Storage. And because it's in Blob Storage, we get this really special property of doing a snapshot. A snapshot looks like this. So first of all, it's a REST API command that we send to be able to back up the database. We're not streaming data. We're just running a command to say, hey, Azure, go snapshot our backup. And you see the syntax here looks slightly different. You use this with file snapshot option. We'll use this REST API. So how do we make sure everything's consistent? What we do is internally in SQL Server, we freeze all IO. We then run the snapshot command. Azure very, very quickly creates a snapshot, which looks like my MDF file, except it has a timestamp on it. And the size of that snapshot is just a delta from the base file itself. So there really is no backup file, although technically there's a small backup file that has metadata. What we're really doing is making a backup of SQL by just making a copy, a differential copy in Azure, and Azure does all this work. When we're done with the snapshot, we basically thaw IO and SQL Server proceeds. It's really, really amazing technology. Instead of streaming backups, we're just saying, hey, somebody make a copy of our backup. Now, how does that apply to hyperscale? Well, first of all, because of the fact that we're doing these snapshot backups, we have no impact applications. The freeze IO operation, that applies to the page servers. Remember, Denzel said that a page server is tied directly to a file in Azure Storage. So the primary compute doesn't even know this is going on. Now, what about this point-in-time restore concept? How is this even faster? Well, think about this. We know, based on the point in time you picked, where the snapshots are that we have to use. And so what we can do is we can start at the LSN of the oldest transaction that we need, which is based on these snapshots. And what we're going to do is, because of the fact that you're going to create a new database when you do a point-in-time restore, we know in long-term storage for the log how much log we need to pick based on the snapshots themselves and what's in the transaction log that's the different changes that are not in the snapshots. Well, how do we do this? Well, it's pretty interesting. Because you're creating a new database, we're able to, in a parallel operation, copy these snapshots and the piece of long-term storage we need into a new set of storage components for this new database. This is why it can be a very quick or constant time point-in-time restore. And then we just need to put the rest of the pieces together. Page servers get seeded. The long-term storage, the log service is going to feed into our landing zone. And then when primary compute is up and running, it can run recovery on the long-term landing zone itself. Why is recovery faster? What if there are a bunch of inactive or transactions that have not been rolled back? We can use accelerated database recovery, which makes undo recovery lightning speed. So the combination of snapshot backups and accelerated database recovery makes point-in-time restore ridiculously fast. Let me show you an example of a demonstration of snapshot backups. Not exactly an Azure hyperscale, because that's behind the scenes, but what does it look like if you do this yourself? Okay, I've got an Azure VM running SQL Server, and you see right here, I'm using that syntax so that my log file and my database file are in Azure Blob Storage. That's called SQL Server data file, or SQL Server files in Azure Storage. So over here, I show commands of a backup to URL. Now that's the streaming backup. Now it's a 100 gig database, but it only takes about 7 gig. So what I get is a 7 gig backup file in Azure. But when I use this file snapshot backup, it doesn't take 3 to 4 minutes. I'll execute it here. It takes seconds. Why? In fact, look here, it takes less than a second. Well, why is that? And you notice here it says process 0 pages, because we're not streaming anything. There's no pages to process. We're just sending a command so that Azure will make a snapshot for us. Now, if I go over and look at something like Storage Explorer in Azure for my storage account, I can see here what is inside the storage account. Now, this is the backup file. I'll have to zoom in to show this to you. This right here is the backup file that I did for the streaming storage. And if you look over here, you can see the size of this is about 7 gig in size. Now, if I go ahead and refresh my storage, you'll notice here I've got something in addition. Here's my data and log file. Remember, these are files in Azure Storage. And here is another backup file. Now, this one is smaller. This one you see here is only 512K. And the reason it's smaller is because this is just metadata that we have about the snapshot backup. Well, where are these snapshots? Well, if you click on the MDF file and say Manage Snapshot, you will see there's another version of the file itself, of the data file. So think about this. We're not streaming backups into Azure Storage. We're just telling Azure, create a version of my file in a point in time that I can use later. And again, these are just differences. So in this particular case, when this snapshot was taken, there's not a lot of difference between it and the base. As more changes are made, my snapshots will become slightly larger because it's differential between what's in the base blob. So a great example of snapshot backups, and behind the scenes, we're using this technology to make hyperscale pretty amazing when it comes to backups and point-in-time restores.
Hyperscale is just a tier of another tier of Azure SQL database. The engine is common SQL Server best practices apply. In addition to this, we'll cover some specific performance and scale tips for hyperscale. One thing to keep in mind is Tempdb and RBPX are finite resources. Given they're on local SSD, they're proportional to the vCore size that is for the service objective. So Tempdb, for example, running large transactions or large temp tables in Tempdb, or even doing offline rebuilds, you can run out of Tempdb. So for maintenance, one of the best practices is using resumable index creation to create or rebuild indexes where possible, because that does it in smaller transactions. Saves on running out of Tempdb. Otherwise, your only option is to go to a higher tier. For offline index builds, another thing which is very common is, so log generation rate on Azure is a commodity. So doing things that maximize log generation rate is recommended. So offline index builds, controlling max DOP indirectly affects log generation rate. If you hope to achieve, other workload going on while you're rebuilding your indexes. So that's one thing. The other thing is, beyond 16 cores for offline index builds, you run into log, contention on latches. And so for offline index builds, in particular on large tables, because Hyperscale can support this large volume, consider having a max top hint of 16 or less. The next thing is, in-memory OLTP is not available on Hyperscale as yet. We are striving to achieve parity, but memory optimized table variables are still available. So Tempdb Contention again, and this is a factor of having larger databases. You don't have direct control over number of files in Tempdb, while we have a great default. And there are cases for certain set of workloads where you can hit contention on system pages of Tempdb. Using memory optimized table variables is a great way to alleviate that Tempdb contention. And then, like we talked about log generation rate, while Hyperscale can support larger sizes, using compression where appropriate, whether it's column store, if it's an analytical workload doing aggregates, or page compression or row compression if it's more of an OLTP, does save on log generation rate, because on an ingest, if we take an ETL operation, if you're ingesting directly into compressed row groups in column store, what you're using in terms of log generation rate is far less than if you are to ingest into a heap. Similarly, with page compression, you can maximize that log generation rate. And then when ingesting in bulk, use bulk copy, and some of the other compute engines like ADF and Spark. Scale up and scale down and adding replica latency is trivial. It's 60 to 90 seconds. It's irrespective of the size of data. So separation of compute and storage does enable that. And so some of the cost optimizations can have to do with scaling up and scaling down at non-peak periods as well. And then some operations, while you hear a lot about it's a constant time operation irrespective of size of data, there are certain operations, for example, cross-region database copies or geo restores, which are size of data, because we have to copy the data across a region. So things like DB copy within region are created with snapshots, like Bob talked about backups being snapshots. A DB copy within region is also from a snapshot. So is a pitter or point in time restore from a region, but cross region, they are size of data operations. So here are some performance tips. On to some of the innovations and future. We have just announced reserved capacity or reserved instances, which is a price optimization in October. There was a few weeks ago. Currently in public preview, we have TDE BYOK, or customer managed keys, which was available in other tiers, and just Hyperscale did not have it from a parity perspective. Database copy is now in preview, in public preview. In region, as we just mentioned, copies are fast because they're based out of snapshots. Cross region, it's the size of data copy. Pitter greater than 7 days. Currently, the retention default is set to 7 days. There are customers who are blocked by it. This will be coming soon. I have no exact dates to announce, but we are hoping to achieve parity. So is geo-replication. Geo-replication today is in, we have it in private preview. We should be in public preview, shortly. We have ongoing work to close all the other feature parity gap. There are no dates to announce. We're working hard to close parity gaps. So your transition, if you want to scale between tiers in Azure, is not a function of features. And then last but not the least, Hyperscale enables some large sizes. We have some aggressive scalability improvements that we're making at all layers, storage layer on up. So lots of investment on Hyperscale, and excited to be a part of it. So Bob, what do you think of the future of Hyperscale?
Denzel, there's no question, if you think about everything we've presented, that Hyperscale is the future architecture for SQL in the cloud. I mean, we're using the power of SQL Server plus this scalable tiered architecture in a very innovative way to do some amazing things for applications. We've seen customers already be successful with that. I warned you, everybody, this would be a hyper session and hyperscaled fast. And we put a lot of information at you in a very quick time frame, but 400 level sessions to pass, just have that reputation. But here's some resources for you. If you want to go just try Azure SQL, you've never tried it before, look at these various resources, whether it's Microsoft Learn or looking at videos Anna Hoffman I've done on YouTube, or even looking at our GitHub workshops. And when you get the slide deck at the bottom down here, you can see these are resources. The deck itself is on AKMS Bob Ward MS. Bob SQL demos are some of the scripts that I did. Unfortunately, some of the demos and scripts Denzel did, of course, internal, we can't share those. And in this deck, when you get it, there's some great links Denzel has for you in the notes section about other information about Hyperscale. And you got to do a shameless plug when you do a session, right? So I have this book that's been released called Azure SQL Revealed, and it includes Hyperscale in it. I was just very, very proud to have Scott Guthrie wrote the foreword for the book. All sorts of people, including Denzel, show up in this book. I think you'll enjoy reading the history of Azure SQL and learning more details of all aspects of Azure SQL itself. So thank you so much for joining us. We really had fun putting this together. We hope you enjoy the rest of the time you're having at the PASS Virtual Summit 2020.